So, good morning. So, we will continue the lecture where we stopped in the last lecture aspect, and this is about the clutch system design. We have been covered. These are the topics. Currently, we are doing with the dynamic analysis, and in fact, we are doing the problem, right. So, I am sure you would remember we have done halfway through. The torque is given 220 Newton and the power 138 kilowatt and operates between 4400 rpm to 7000 rpm. These are the gear ratios and final ratio. It is asking to find out right for a 10 up and down shifting cycles of a clutch, and it is a single disc clutch. The only information as a clutch design engineer, we are given the freedom for you to choose a bronze base sintered with the cast iron friction lining aspect, okay. And also the tire diameter is given. In fact, this is the table. In this table, what we have done, we have chosen the pressure. This is the bronze sintered. So, this is the given pressure and the temperature and the corresponding dry lubrication, because this is a single disc plate, right. So, it has to be dry. If it is a multi disc clutch, in the sense you can have a oil lubricated. So, since it is a disc, single disc, dry would be good, and we have chosen the mu equal to as a maximum 0.4. You can choose, depends on how do you want to, and pressure we have chosen as a 1.7 into 10 power 6 Pascal or Newton meter square, okay. This is the value I have chosen, and also based on this value we are able to find out the dimensions. Hope you remember dimension D we have taken as a 100 millimeter inner diameter of the clutch. The outer will be 0.17 or 170 millimeter. So, this is what we have done that, and we have try to carry out the velocity table, right, to find out the for the vehicle for different gear speeds. That is where we stopped in the last lecture. So, we will continue. So, the gear, we will have a gear number and gear ratio, okay, and the overall speed, then the vehicle speed, right. So, this is gear ratio means Ig, overall IO, right, and VI is the thing, you know, this P dW, one speed I said 60 into IO, this is the formula, right, yeah. This should be in meter per second, this should be in meter per second. In fact, I asked you a question, what speed should we choose? Should we choose the maximum speed 7000 rpm or 4400 rpm? Which one we have to choose? That is what the question where I asked you. Did you find answer for that? Any answer? Right, 2.786, 1.614, 1.082, 0.773, then 0.566. This is the gear ratio, and overall final drive ratio is given. IF is given. IF is given 4.44. This is your final drive ratio. So, with that we got to 12.37 as overall ratio, 7.166, 4.701, 761, 3.432 and 2.513. Of course, the reverse also there, but we considering mostly for forward speeds, not the reverse speed, okay. Yes, question. So, which speed are we going to do that? Is it engine speed? So, of course, it is engine speed. Is it for the maximum power condition or maximum torque condition? That was the question. What is the answer? torque, maximum torque condition. Okay, that's what you mean to say that. Okay, maximum torque condition. What is the reason behind why you want to do maximum torque? Clutch transmit the torque. Okay, but that is placed between your flywheel and the gearbox, right? Any specific reason for the torque aspect? That's the question. Yeah. Indeed, it's correct. So you can go with the maximum torque condition aspect. Maximum torque condition aspect. You can go with that. Okay. You can have two approach. One is this the torque aspect. Otherwise, if you want to understand the maximum possible heat generation, in that case you can go for a maximum speed also, maximum power condition. Two way you can solve. So, however, so I am going to solve with the this the maximum torque condition. I am going to do that. Okay, the maximum torque condition I am going to do that. So, N will be, what is that? N will be 4400 rpm, that is the maximum torque condition. Yeah, is the engine speed, of course, is the engine speed. This speed for T max. So, what is the T max is given? 220 Newton meter. So, this is what the things, 220 Newton meter. So, in that case the VI would be, and I am sure we know this equation which we did similar to the gearbox, V equal to R omega, right. So, this is 13.037, 22.505, okay, 33.874, 46.99 and 64.174. So, now we got this velocity table for the clutch aspect. Okay. So, that is fine. Yeah. Now, ultimately, see what exactly happening when the clutch is engaged and disengaged. During the time the heat is generated. So, we need to find out what will be the maximum heat, okay, whether that is within the permissible limit from the table. Based on that, we are going to do the validation of the clutch design. Okay, validation of the clutch design. I just wanted to make sure that you would remember certain equations, which I already explained in at the beginning. Okay, 3 equations. Remember the moment of inertia, I is at, right, I said Km Em, right, V square omega square. This is the equation, right. This equation we are going to use it. That is for a moment of inertia, because they are rotating components, right. So, to convert that, what we have used V square by omega square we did. Km is we can choose as a 1.2 for taking 20% additional inertial effect. Km we choose as a 1.2. What is the mass value? It's a 15.7, right, 15.7 kilonewton. So, 1570, so much kilogram. So, that is your mass. So, this is the equation we are going to use it. Then the another equation which is talking about the torque. What is the torque? We need to find out the load torque, right, TA, or acceleration torque we need to find out. So, the acceleration torque we have to find out is equal to it is nothing but engine torque by load torque, right. It is engine torque by load torque, which nothing but I is at omega 2 minus omega 1. These are generic equation, right, by T, the slipping time. Or else acceleration time, both ways is there. Then another equation we need to find out your same thing, a slipping time aspect, Ts equal to I is at omega 2 omega 1 Te by TL. So, this is the equation we have. So, this is I will tell you what does that mean omega 2 minus omega 1, and similar the heat generation Qs equal to Iz omega engine, right, or we can say omega 2 minus omega 1 whole square by 2 into load factor T minus TL. So, these are the equation. So, I think these are the equation already I have explained. This is for the heat generation per engagement, this engagement. Okay. This heat for the engagement. So, based on this we are going to calculate for each gear what will be the heat generation. That is what we are going to do that. Yeah, that is what we are going to do that. And okay, then there is one more load torque. We need to find out load torque TL equal to mu r, right, mu r mg VI by omega. So, this is the equation where mu r equal to is your air coefficient, right, rolling coefficient, rolling resistance, the rolling resistance. Generally, if value is not given, it varied to 0.2 to 0.3. So, in our calculation we will choose mu r equal to as 0.02. So, this is the value we are going to use it and try to solve the problem. Okay. Yeah. So, now first thing I will explain how to find out the moment of inertia, but the moment of inertia we need to find out. I am going to give you only one step, then we will go for a table. The first thing for first gear, all I am going to do for the respect to the first gear aspect, right. We have to find out the Iz, the moment of inertia 1.2 m Vi is engine speed with respect to engine speed, right. So, this is the thing. So, engine speed, what is the engine speed? 2 pi Ne by 60, yeah. So, 2 pi into 4400 by 60, that should give me 460.77 radian per second. So, this is the value you got it, right, this is the way you got it. And I is at 1.2, the mass will be 1570. What is the VI? VI means what? The velocity I means corresponding to the gear, first gear. What is the corresponding to the first gear? The VI 13.037, right, 13.037. So, 13.037 whole square by 460.77 whole square. Could you please tell me what is the value you are getting I is at? What is the value you are getting? Are you getting 1.5375? Yeah, 1.5375. So, that is your I is at. Okay. For the first gear, everything we are doing with respect to the first gear. The second one, we need to find out the load torque. Load torque, maybe I will go to next slide. Load torque TL, it is again mu r mg Vi omega E. So, this is the thing. So, mu r is nothing but 0.02 and the mass 15700 it's like a W, so weight. Then Vi 13.0, right, 13.0, right, look at 037 omega 460.77. So, tell me what is the value you are getting? Are you getting 8.885? 8.885, so much Newton meter, that is your load torque. That is your load torque. Now, this fine. So we got low torque. Okay. Now next thing is we need to find out the time, slipping time, where when they engage, right. So how much time is taking to attain the relative speed equal to 0. So the engine run at one speed, so the gearbox run at one speed, alright. Then you are disconnected, it is disengaged, and you want engage. The moment is engaged, so both have to have a relative speed 0. That means whatever the driven member, right, will attain the drive member speed. That's what it meaning. So we need to find out what will be the timing. Okay, the slip time. So again, I will rewrite the equation for a better understanding. Right, is I is it. Okay, I is it omega 2 minus omega 1 by T minus T. So this is the equation. So in fact, I will make it a very better thing is, so this is engine speed omega I is the corresponding gearbox speed. Then you can have a, okay, the T minus TL is nothing but your, right, acceleration torque is nothing but your acceleration torque. Yeah. So I is it, already I know that I is it, I got 1.5375, 1.5375. Engine is 460. Okay, engine speed is 4.77. What is the omega I? What will be the omega I? Right. So what is the omega I? Can you tell me? And your T is T is 220. The load torque already we got 8.885. That is known. Okay, this is your engine torque, and this is your load torque. Okay, what is the omega value? Sorry, 153. Okay. So you can tell me what is the value you are getting then? Yeah. What is the time you are getting? Slipping time, TS RT. So just leave it now. I'll come back that point. Okay, I'll come back that point. Just want to give one more concept. So I need to find out the secondary angular velocity with respect to the engine speed. When the gear is operating at first speed, assuming that. So the equation will be normally the initial velocity, the change in velocity, whatever the corresponding, then your engine speed. This is the equation. Okay. The question is, in the first gear, I don't know what is the initial velocity, right? We don't know that. So obviously, the omega 2 will be 0. The omega 2 will be 0. So what you have to do, you put 0 here and tell me what is the value you are getting. Are you getting 3.356? You should get 3.356. 3.356 is the second. So many seconds slipping time would required in the first gear engagement. Are you getting the value 3.35? Yes, that's the one thing is there. Now this is done. So we have done the time aspect, we have got the load torque also, and we know acceleration torque from the engine when you subtracting from the engine torque. Finally, we need to find out how much heat generated with the respect to the first gear, right? Heat generated. So your again the moment of inertia, right? I alpha square kind of thing, right? So this is engine speed, the whole square corresponding the speed by 2, then the load torque T minus T by TL. So this is happened. So I is it, I know that's 1.5375, engine is 460.77, this will be 0, the whole square by 2 into 220 minus of 8.885, this is the thing. Okay. So, can you give me what is your heat generation? It is happening for first gear engagement. This is should be in joules. So, are we getting 1700, right, 82 joules? This many joules you should expect in the first gear engagement aspect. Yeah, are you getting this value? Right. So, this is the way you do. So, initially find out IZ and a torque, loading torque corresponding the speed, then the time for slipping aspect, then finally you will have a heat generation for the first gear engagement. Okay. So, this is the way you need to do that. In fact, I will do with respect to the entire gears aspect. So, the gear, okay, IZ is a kg meter per square, then your torque Newton meter, load torque omega 2 time and q, right. So, this should be in joules, this should be in joules, this should be in second, okay, and this should be in radian per second. Yeah, this is Newton meter, and this should be what, kg meter square, right? Yeah, kg meter square. The first gear, second gear, third, fourth and fifth. Okay. So, we know this is 1.5375, that is what we got, and 8.885, and this should be, yeah, I will rewrite again, omega 2 equal to Vi plus 1 into omega engine speed, okay, E, that is the thing. T already we know, Qs already we know that, okay. So, this should be 0, this should be below 3.356, 170,082 joules, that is what you are getting, right. So, now you have to find out for the second gear. In the second gear, Vi will change, Vi value, again we have to refer your Vi from the with respect to second gear, it should be 22.505, that is a Vi. So, when you substitute, you will expect the value 4.5814. The torque also Vi will change, right, Ti equal to, sorry, TL equal to mu r mg Vi omega engine speed. So, the corresponding Vi substitute, obviously as the velocity increases your load also will increase, right, torque load will increase 15 Newton 0.3375. The omega 2 with respect to the previous speed will be 460, right. Then whatever the Vi, right, that when you subtract, when you take the ratio, now you know the two ratio. The first will be, what will be the first speed? 13 point, the first gear speed. Now we are changing with the first gear to second gear. We are changing from the first gear to second gear. So, the from the table if you refer, the Vi would be 13.037, right, 37, then Vi plus 1 would be, what is that value, 22.505. So, that is what you have to substitute with the engine speed, then omega 2 you expect, you will find out the omega 2, that should be 266.92, okay. Similar way, if you find out, do for the your time 4.339, then you will get the heat generation 95,529. So, if you repeat the same format, you have to keep changing the velocity of the vehicle velocity for the corresponding gear, alright, and find out the corresponding change in angular velocity with respect to the previous gear. If you do that, then finally you are able to find out the slipping time as well as the load torque and the heat generation. 10.3. So, I am going to give right away the values, since I explained for the first two gears now it is easy for you to follow it up. Okay, 30123. This is should be 8152. 138,674. That should be a heat. Then here 19 point for fourth gear, 19.73. This is the 23.085. Yeah, this should be 32.024, 332.158, 13.665. Okay, 100,473. For fifth gear, the fifth gear 37.253, 43.735, 33.389. Then the slipping time is 26 second almost. So the heat generation 3053, 903. So this much heat generated happening. So if you do the summation of the total heat generation of all 5 gear shift, right, second gear, third, fourth and fifth, right, that should be 8058, right. So 858,661. So that much heat generated for one operating cycle. It's called one complete operation, one up. So usually when you gear engagement, right, when clutch is engagement, you will go from first gear to maximum gear. You are not doing in between, right. So first, second, third, fourth, fifth and so on. So that is the first cycle, one up. And if you want to reduce the speed, will you straight away go to first gear, or how will you do in general? You have to step down, right. So again fifth, fourth, third, second and one. So one operation of clutch will be one up cycle, one down cycle. In fact, if you look at the problem, clearly says for 10 cycles up and down, 10 cycles up and down. So that means 10 into 2 times, 10 into 2 times. Yeah. Now we got the complete the table aspect. Okay. So this is the total heat generated per engagement. The total heat generated per engagement (8,058,661) so much joules. Okay, but we want to know the total heat generation, right, per hour. The total heat energy generated per hour. This should be QS, right? This is QS. We want QH, QS into number of stroke, number of cycles, number of cycles. Well, say the number of cycles. (858), right? 6661. So what is the problem is given? What is given in problem? Number of cycle you can take it as a n also. Maybe this is QH into n. 10 cycles, right? In the problem is given 10 cycles. 10 cycles up and down, 10 into 2. So that is what is given. So if you do that, so we would expect 17,713.232 so much kilojoule per hour. Okay, but we want everything with respect to kilowatt. So when you do that, okay, it will be 4.47 kilojoule per second, right? Or else you can have a 4.47 so much kilowatt. So this much heat is or power loss happening during the engagement. Okay, this is what happening. Okay, so the question is how are we going to verify it? That is the question, right? Now we got it. So we got the total heat generated for the entire clutch for 1 hour. Yeah. Okay. So but we don't know dimensions, right? We don't know still other dimensions. So that's where we need to understand what exactly is happening. Okay. So what we are going to do. A little bit mathematical thing. We know that this is our QH, this is total heat generated, right. Then we need to this one verify with the heat transfer, it's a right. So A alpha A delta T, this is the temperature rise, A is the surface area of the clutch, alpha is the heat transfer coefficient, heat transfer coefficient. Surface area of clutch and the temperature rise during the operation. So, we need to find out the alpha, what is the alpha, and find out the area. Okay. Then we'll from there we'll find out the what is the temperature is going to be during the heat generation. Okay. But to do that, then the problem is solved. Okay, then the problem is solved. So just I want to give some guidelines. So already we know what is the D. What is the D? 100 mm, right? Clutch inner diameter. This is the outer diameter, and what is the outer diameter? 170. Am I right? Yeah, 170 millimeter. So these two dimensions are known to us. Okay. So now we'll see the guidelines for clutch assembly. This A will come through the your assembly dimensions. Okay, alpha I will do later. So the pressure plate thickness, usually you can take how much pressure plate thickness. You have seen the dimension, right? Generally pressure plate thickness can vary maximum of 15 millimeter. You have seen the thick plate, right? The pressure plate where a diaphragm is attached, that is it will give 10 to 15 millimeter, the pressure plate thickness. Okay. And the clutch plate thickness, clutch plate which is nothing but your friction plate, clutch plate thickness right, you can have 10 to 12 mm. And the cover thickness is again where the pressure plate and clutch plate all together, that can be taken as a 10 mm. Then based on that everything will change. Perhaps I can draw small diagram, so that you will be able to see what exactly you want to do that. Right. So assuming that this is your friction plate, right? This is the friction plate. Then this entire thing will be attached with your pressure plate. Yeah, you will have one more pressure plate. Okay. Just give you the identity. This is your pressure plate. Then you will have one assembly cover. When you will have assembly cover, okay. In fact, I should do the proper way. Okay. This is your friction lining, right. So this is your inner diameter and this is your outer diameter, yeah, that is given. Then you will have a pressure plate also, but pressure plate also will be a solid with the hollow thing. Then on top of that you will have a clutch plate. The clutch plate again there will be a there will be a opening. Hope you have seen diaphragms. When you see the diaphragm thing, right, there is always this place is for the heat dissipation, that is for dissipation, whereas the heat transfer is happening on this side and the circumference side. So this surface and the circumference surface, because ultimately we need to find out what is the total heat transfer surface area. Okay, That is where we are heading now. Now the clutch cover, okay, the clutch cover what we can have, outer dia, right, outer dia. So whatever the you are having OD of the your clutch plate, with that we have to give the clearance. We will give the clearance both sides. The OD of the clutch plus 15 plus 15. Okay, this is the allowance. This is the allowance. So this is for a clutch cover outer dia aspect. Then I will move to another slide. Clutch cover surface area, which is nothing but A, right. The clutch cover surface area, what is the circumference, what I said, the circumference, clutch cover diameter, right, into total thickness plus what else you have. Remember I said like this, this is a one is the clutch plate, this is a pressure plate, then you will have a clutch cover, okay, a clutch cover like this. Yeah, so then we will have a clutch disc area also, that is also altogether that will be a total surface area, that will be total surface area. So can you find out what will be the clutch diameter now, clutch cover outer diameter? $170, right, 170 is outer dia, and we are giving allowance 15-15, right, 15-15 outer and inner, that should give us a 200 millimeter, okay, that is clearly given 200 millimeter. And how about the thickness, what about thickness, how about thickness? So your clutch, you have to think about your friction plate thickness, pressure plate thickness on top of the allowance, on top of the allowance. So clutch plate already we have chosen, the thickness of clutch plate 15 mm we have chosen, clutch plate thickness maybe 10 to 12, we can choose 10 mm also, does not matter. Then you have a pressure plate 15 mm, then a cover thickness you have another 10 mm, okay. So how much you are going to get this aspect, yeah, the thickness aspect, how much you are going to get. See, you need to find out the clutch cover dia, okay, this is what happening, and the clutch disc. So for me is much easier, for I can get straight away 5 by 4 d square minus d square, that is the area I will get it. The d would be right, here is going to be the clutch aspect, so 200 mm and the d will be 100 mm, so that is fine. My only concern about the clutch cover diameter aspect, clutch cover and the total thickness. How much can we have thickness, right? How much can we have? This is 5 into 0.2, right, how much can you do? Yeah. Yes, what is that? No. Look at this, I am talking about this is your thickness, because this is also surface area, right. So that thickness we need to know that, right. So clutch plate already given 10 to 12 mm, then pressure plate already given 15 mm, that itself give you 27 mm. So what else, right? How about the clearance? What happened to clearance? right. So because we need to allow the heat dissipation also. So I'm going to check totally. I will take it as a 70 millimeter total together. I will explain maybe later. So let me finish this one. So I'll choose as a 0.07. Okay, 0.07. So much dia. Okay, the whole square things. No, sorry, not so this. Sorry, not the square. So can you tell me how much is getting your how much your surface area getting? Cut surface area. You should expect 0.067 54 so much meter square. This is your surface area. Okay, this is your surface area. Now, I'll explain. Okay, let me do that. Yeah. Then I need to find out the here. As you see that this heat transfer, the equation, I said QH equal to alpha A delta T, right. I need to find out the alpha heat transfer coefficient. Heat transfer variable coefficient. Okay, that's fine. This alpha, okay, we need to find out. Here to the alpha is nothing but there is a numerical equation 12.8 into 2.9 velocity. So straight away take the equation. This is taken from the heat transfer aspect. So we are not going to look at how the equation arrived. That is not our purview. Our purview, you just use the equation. Yeah. So this is the equation. Then the V is the velocity. V is the velocity because the clutch cover also is happening, which nothing but your engine speed into rate RC. RC means the radius of clutch. Radius of the clutch. Okay. So engine speed we know that omega E equal to 460.66 radian per second. That we know that. RC already we got 200, right? 0.2 meter. That is clearly given, right? From that, if you find out the velocity, right, is easier. 12.8, 2.9. So I'll say that 460.66.2, right. So if you do that, I would expect the alpha would be 1202 so much joules per meter square per second, okay, per Kelvin or per degree Celsius. This is what happening. Okay, alpha is covered. Sorry? Okay, RC is 0.1, is it? Okay, then what is the value you are getting? Sorry, I made a mistake then, yeah. That is DC, right? Yeah. So what is the value you are getting? So what? 146.3. Okay. So this is given, right? So now QH equal to alpha A delta T. We need to find out delta T. Okay, delta T equal to QH by alpha area. Okay, what is QH? QH already we know that we got how much we got, that is 447. Okay, that is we got it. Alpha we know 146, right, 0.3. Surface area we know. What is the surface area we got? The surface area we got point, right, yeah, 0.06754. Yeah. So what is the delta T you are getting now? Can you find out delta T? Delta T please. Submit 4.7. Okay, this much degrees Celsius. So you can assume this ambient temperature, right? Ambient temperature I can choose as a 35 degrees Celsius, right? So then the one T max, the T infinite, that will be 48.7 degrees Celsius. Then T max, what will be T max you would expect? 482.7. I'll take 35. Okay, together that should be 0.7, right? 7 and 1 and 600. Okay, the maximum heat generated you are expecting 617 degree 0.7, so 617.7 degree. Okay. Yeah. So okay, question is, so what is the maximum temperature you are expecting if you use the asbestos, sorry not asbestos, sintered, right, sintered based cast iron friction lining? What is the maximum temperature you are expecting? The table, what is the maximum temperature? Look at the table we have chosen. Maybe can you go back to the table? What is the maximum temperature range you are getting from the table? Okay, so maybe I'll keep it. Right, let me go again. Look at what is the temperature you are getting? 232 to 677, right? 677. Okay, so what is the temperature you are getting here? This is less than your allowable time, right? Allowable temperature, right? What is the allowable temperature? That's what you see. Allowable is between 236 to 676. Yeah. So is it safe or not? It's safe. Hence, the clutch design is safe. Okay. The question is, if the temperature exceeding, what is the solution now? If the temperature exceeding, T max we got within the allowable limit, that is fine. If it is not within the allowable limit, it is exceeding, then what is the next solution? What will be the, how will you approach? Either change the material, that is one way to do that. You can change the friction value. Okay. The second aspect, how about changing the dimensions? That is another approach, right? That is how you can do that. Yeah, I think I will stop now.